This is the third video in the Pure Math 1 course on geometric series, and it deals with the sum to infinity of a geometric series and also convergent and divergent series. Okay, suppose we have a piece of string and it's 2 meters long. So that's 2 meters. And we cut it in half. So we've cut it there. So what we've got now is 2 pieces of string of both 1 meter. So that is 1 meter and 1 meter. Now supposing I take the second of the 2 pieces and cut that one in half. So we cut it in half there. So now what I've got is a 1 meter, and then a half a meter, and another half a meter. 1, a half, and a half. And now I'm going to do the same again with the second of the half meters and cut that in half. So I'm going to have a 1 meter, a half meter, and then 2 quarters, like that. 1, a half, a quarter, and a quarter. And I'm going to cut the second quarter in half, like that. And now what I've got is 1 and a half, and a quarter, and 2 eighths. So that's 1, a half, a quarter, an eighth, an eighth. Well, let's do that again. We'll cut the second eighth in half, like that. And we'll have a 1, a half, a quarter, an eighth, and 2 sixteenths. And we can continue. I can cut the second 16th in half, and we'll have 1, a half, a quarter, an eighth, a 16th, and then 2, which are 1 over 32 each. And I can carry on. I could cut the second 1 over 32 piece in half, and that will give me 2 1 over 64 pieces. And I can carry on and on and on. There's no limit, theoretically, to the number of times I can cut the string in half. I'll just get smaller and smaller pieces. I mean, it would be obviously very difficult to cut actual pieces of string in half when they get tiny, but in theory I would have infinitely many pieces of string. We start off with a string of length 1 meter, and then we have a second length of a half, and then a quarter, and then an eighth, and then a 16th, and then 1 over 32, and then 1 over 64, and then 1 over 128, and it would continue indefinitely, and we'll have infinitely many pieces of string, and each one becoming infinitely smaller, very, very small, and closer to 0 length, but never quite getting to 0 length. So we have this series of numbers which never ends. Now, that is what we call an infinite series, because there's no end to it. But what is the sum? Well, we started with a piece of string of length 2 meters. So even though there's infinitely many pieces of string, the total amount of string is still the same. So the total of this sum should still be 2. So what we have then is an infinite series with a finite sum. Infinitely many numbers in it, albeit they are becoming vanishingly small, very, very small, but infinitely many nonetheless, but a finite sum comes to an actual number 2. Now, when an infinite series does this, we say it is convergent. So if an infinite series has a finite sum, as in this case, then it is convergent, as I said. On the other hand, we can have a series like this, 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64. This is a geometric series. We're multiplying by 2 each time. Well, this clearly doesn't have a finite sum. We can see that each term in itself is getting bigger and bigger, so the terms themselves, as we carry on, will be infinitely big if we carry on indefinitely. So the sum is definitely infinitely big, and this we call a divergent series. So an infinite series which doesn't have an infinite sum is divergent. Now, it's not always obvious, in fact, whether a series is convergent or divergent. It's quite clear that this one, 1 plus 2 plus 4 plus 8, etc., is divergent because the terms get bigger and bigger and bigger. But for instance, if I wrote 1 plus a half plus a third plus a quarter plus a fifth plus a sixth, like that, so that is the sum of the reciprocals of the whole numbers. That's actually called the harmonic series. This is in fact divergent, even though the terms get smaller and smaller, and they get for infinite terms, the terms go towards 0, but this is in fact divergent. Now, why that is divergent is outside the scope of the syllabus, but I mention it to say that it isn't always clear when a series is divergent or convergent. A geometric series, however, is always convergent if the common ratio r is between -1 and 1. Otherwise, it is divergent. This one here, the sum of the where we have first term 1 and the common ratio a half, we can see is convergent because we have the finite sum is 2. So this one here, on the other hand, where the common ratio is 2, which is more than 1, bigger than 1, is divergent. If r is equal to 1, well, if we a geometric series where r is equal to 1, and say the first term is 1, would look like this: 1 plus 1 plus 1 plus 1 plus 1 plus, and we're adding 1 because we multiply 1 by 1, we just get 1. So we're adding 1 infinitely many times, or infinitely many ones are infinity. So that's divergent. That's when r equals 1. But what about if r equals -1? Well, if we start with 1, now multiplied by -1, we'll get -1. So adding -1, take away 1. If we multiply -1 by -1, we get +1. If we multiply +1 by -1, we get -1. And so on. We'll carry on in the same way. So we get a series alternating plus or -1. And we carry on like that. Well, clearly that doesn't go to infinity, because if we think about it, 1 minus 1 is 0, plus 1 is 1, minus 1 is 0, plus 1 is 1, minus 1 is 0. As we carry along the series, the sum alternates between 1 and 0 depending on how many we have? Well, if we consider an infinite series of 1s and minus 1s and add them up, we can't know whether we have a sum of 0 or 1. So we don't have a finite sum because we can't say which it is. So this is also divergent because we don't have a sum. So we find that we have a geometric series. Geometric series are convergent if and only if r is strictly between minus 1 and plus 1, not equal to minus 1 or plus 1. Now, in a previous video, we saw that the sum to n terms of a geometric series is a into 1 minus r to the n over 1 minus r, if r is less than minus 1 and less than 1 and greater than minus 1. Well, that's the sum for any r, but let's have r between minus 1 and plus 1. Well, what happens as n tends to infinity? As n tends to infinity, in other words, we make n get bigger and bigger and bigger. Well, r, because that is a fraction smaller than 1, to the power of n, will get smaller and smaller and smaller. Let's consider r equals a half. Well, if we just have a half to the power of 10, we get 1 over 1024. A half to the power of 100, using the calculator, is about 7.9 times 10 to the minus 31. That's incredibly small. So when you raise a half to large powers, it gets incredibly small, very, very small, and as n tends to infinity, we'll have r to the n, I should say, tends to 0. So the sum, which we'll call the sum to infinity, like that is a symbol for infinity, is equal to a into 1 minus r to the n. Well, r to the n becomes 0, so we'll have a over 1 minus r. So a over 1 minus r is the formula for the sum to infinity of a geometric series. The sum to infinity of a geometric series, where r lies between minus 1 and plus 1. This is often written like that. The modulus of r, which is the positive value of r, is less than 1. So we must also have that condition. So here's some examples. First of all, find the sum to infinity of 1 plus a third plus a ninth plus, and then we have infinitely many terms. So a is 1, the first term, r is a third, the common ratio. The sum to infinity is a over 1 minus r, or 1 over 1 minus a third. 1 divided by 2/3 is 3 over 2, or 1.5, 1.5. Second example, the third term of a geometric series is 4, and the fifth term is 1. Find the sum to infinity. Okay, well, we need to find the first and the term and the common ratio. Now, we know that the nth term, un, is a r to the n minus 1. Now, we have the third term, that's 4. So u3 is 4, and we have the fifth term, u5, and that's 1. So, a r to the 3 minus 1, or a r squared, is 4, and a r to the 5 minus 1, or 4, is 1. Two equations we can solve simultaneously. If we divide 2 by 1, a r to the power of 4 over a r squared is 1 over 4. and so the a's cancel. R to the 4 divided by r squared is r squared, so r squared is 1 over 4. So r is, well, it could be plus or minus a half. So there's two possibilities for r. R could be plus a half, or r could be minus a half. If r is plus a half, well, we have ar squared is equal to 4. Well, r squared anyway is always a quarter, so we have a times a quarter equals 4, so a is 16. So a is 6, the first term is 16, whether the ratio is a half or minus a half. But if r equals plus a half, the sum to infinity, which of course is a over 1 minus r, would be 16 over 1 minus a half. So that's 16 over 3 over 2, which is 32 over 3. But if r equals minus a half, the sum to infinity would be 16 over 1 minus a half. Wait a minute, mistake here. 1 minus a half, of course, is a half, so and 16 divided by a half is 16 times 2, which is 32. So apologies for that. In the second case, where r is minus a half, 16 divided by 1 minus a half is 16 plus a half, which is 3 over 2, and this time we have 32 over 3. So two possible answers for that problem. Okay, now return to Study Smart, where you'll find an exercise to download where you can practice problems on geometric series. That's the sum of geometric series and the sum to infinity.